He is a true pioneer for this field. His research in StreamDiffusion inspired a whole open source community of creative technologists and applied researchers, gathering over 10,000 GitHub stars just within a few months of launching. Now, he has continued this research work and recently released StreamDiffusion v2, which improves on v1 in the temporal consistency and the world understanding. And he's also going to be a professor at UT Austin starting next fall, which I'm very excited about, because it's going to be 10 minutes from my house. But without further ado, I want to introduce you to Chenfeng.
Yeah, thanks. Thanks for the great introduction. And today I feel very excited to share our research, StreamDiffusion, with you. Through this talk, you will learn how I utilize the knowledge from machine learning and system to solve the efficiency problem in streaming application. And let's get started. Current video generative models are revolutionizing the content generation. For example, we could easily utilize a text prompt to enable the video generative model to generate very fancy and realistic videos. However, current video generative models are very inefficient. For example, it takes more than 10 minutes to generate a 16-second video with 8 H100 GPUs. This inefficiency makes us hard to utilize it for streaming applications. On the other hand, current video diffusion models are designed to generate a whole bunch of frames at a time and make sure the output video done under a chunk of time. But for the streaming application, it requires the output to meet every deadline. This means that the input is streaming comes in, and we need to smoothly output what users want without loss. So we propose StreamDiffusion to resolve this issue. StreamDiffusion is a pipeline-level solution to transform current video generative model to cater to the streaming applications. So it enables some new capabilities. For example, this is one demo from our StreamDiffusion. It enables the users like me who never learn how to paint beautiful art image. So I can just sketch on the iPad, and our model can transform it into beautiful art image in real time. And this is achieved with just an iPad and a desktop RTX 4090. This was something previous very hard because because the diffusion model can only run 1.25 IPX on RTX 4090. But our model can enable it to run 91 IPX on RTX 4090. So how could we make it? Let me briefly recap what is diffusion model for you. Diffusion model was nothing but just giving some data or image distribution. We gradually add some noise until it transforms a Gaussian or noise distribution. And diffusion model is to utilize a parameter to learn to denote step by step until it transfers back to the image distribution. So this is how diffusion model works. And now we want to consider to utilize diffusion models for streaming application. So that when in the streaming application, the image is streaming comes in. So let's first consider dealing with the first image. So we will utilize the chained diffusion model, deal with step by step. And we can translate the first image to another style. But let's remember, we are considering a streaming application. The second image is still waiting there. So after we translate in the first image, we need to then translate the second image, and also step by step. Apparently, this is very inefficient and underutilize the computational capacity. How could we make it better? Let's try to find some structures in this kind of implementation. So we can try to zoom out and look at this implementation. Actually, it is kind of a sequential implementation. In the sequential implementation, each denoising steps actually can be treated as block sequentially stacked together. And in each block, we would utilize the diffusion model deal with step by step. let's remember, we always utilize the GPU system to deal with the streaming application. And GPU system is really good at parallel computing. So could we utilize the parallel computing capacity of the hardware to accelerate this kind of sequential implementation? So we want to reorganize this kind of structure a little bit to make a full utilize the hardware capacity. We just need to reorganize it a little bit. So we can transform the sequential implementation into a sequential but batch implementation. And we propose stream batch. So in stream batch, we will utilize the diffusion model to deal with the first image. But at the same time, the second image already comes in. But this time, we don't have to wait. We could put them together and deal with them together. At the same time, the third image comes in. We also don't have to wait. We could put these three together and deal with them together. So this can enable us to achieve high throughput and smooth output. But quickly, we find a problem. In diffusion model, we always have a component called CFG. And this kind of CFG will lead to 2 times larger cost. So we want to improve this. Let me first recap what is CFG for you. CFG is classifier-free guidance. So in CFG, if you want to denoise the noisy image into clean image, we would have several steps. The first step is that we want to calculate an unconditioned generation term. And then we will calculate a conditional generation term. And we will calculate the difference between the conditional term and the unconditioned term. And we will amplify this. And we will utilize this amplified term to update the sampling. So you can see that the classifier-free guidance would always have one conditional term and an unconditional term. So it always needs one extra computation to calculate the update term. So this is 2 times more computation. So in our streaming diffusion, we also provide a new technique called the residue CFG. So let me share our insight about the unconditional generation for you. So in diffusion model, the unconditional generation of it always predict the update term with the direction toward the center of the training data distribution. This is to make sure that your conditional generation is not biased to some random distribution to the generation so that the generation could be more stable. But for our case, our streaming application already have a center. This center is our input source image. And this means that we can directly build a trajectory between the noise and the reference image. Instead of utilizing the unconditioned trajectory to stabilize the generation, we can directly use the trajectory between the noise and reference image. So this can help us remove the overhead of the unconditioned generation. So our method, stream batch plus the RCFG, can lead to up to 3.6 times faster speed when we utilize the diffusion model for the streaming applications. So this is the whole pipeline of our streaming diffusion. So we also have the key idea is our stream batch and our RCFG, and we also have some other techniques like TensorRT, IOQ, compressed VAE, cache strategy, and some distillation techniques. So we combine all of them. And finally, we could significantly accelerate the image generations. So you can see on the right video that we can drag elements and move the elements, and we can transform it to beautiful auto image in real time. So our pipeline method is more efficient than open source pipeline method like diffusers from Hugging Face. So compared to the Hugging Face diffuser pipeline, our method can achieve much higher throughput, and this is more catering to the streaming applications. And you can easily utilize our stream diffusion by just piping install stream diffusion TensorRT. And our work gets very popular on Instagram and Twitter, and it has already gained a lot of GitHub stars. And many users utilize our work to create some cool demos. And this is one of our one of my favorite
Sugar
demos.
cubes.
So the users utilize our work to create an AI mirror with voice control.
That's sugar cubes. Light bulbs. Whoa.
Yeah. And there are some more demos. For example, one users from Twitter, they utilize they move their hands, and our work can transform the hand into control the flower generation smoothly. And there are some
try relaxing.
other researchers in the to visualize the brain signal. For example, that the users could equip some devices, and our model can transform into some patterns to visualize the brain activities. And there are also some visualization research. For example, that the chief of innovation at DBT Studio utilizes our work to visualize the physical light. So we can shed light the physical lighting on the table, and our model can transform into the beautiful flower image in real time. This also enables something new in graphics research. So previously, in graphics research, if we want to generate high quality fluid, such as water and fire, this is very expensive. But with StreamDiffusion, we can utilize some fast, low quality render plus our StreamDiffusion to translate into the high quality fluid, such as water and fire here. And I myself also have great interest in robotics research. So I also try to utilize our research work for robotics. So I utilize the StreamDiffusion to translate one kind of robot video to other kind of robot videos. So this could help us to reduce the robot data collection efforts. And this work was also get oral last year in Coral conference. Yeah, so this is our work about StreamDiffusion V1. And I knew LivePeer and Daydream starting at 2025, and I do appreciate that Eric reached out to me, and we have great discussion about their product, Daydream. So when I first looked at Daydream product, I was amazed that they create so many cool demos. So I'm really surprised that this can enable many users can utilize for create their live stream app. So I really like it. But quickly we found a problem that the temporal consistency need to be further improved. So Eric chatted with me and asked Chenfeng, can you make it more temporal consistent? Yeah, and I tried it. So I and Jeff will talk about the work, Stream V2V. So we try to improve the temporal consistency. At another track, I do give the full credit to Xunhuang. He will also talk about his work, the cost VID and self-forcing. So he significantly improved the efficiency of the video generation model. So standing on these two works, I'm thinking that could we utilize the video diffusion transformers to improve the temporal consistency for the streaming applications? And we propose StreamDiffusion V2. So in StreamDiffusion V2, different from StreamDiffusion V1, we utilize the image diffusion model. Now we want to utilize the video diffusion model to improve the temporal consistency. Let's remember, as I mentioned before, previous video generation model is designed to generate a bunch of frames together, under a given chunk of time step. But for streaming application, we need to make sure the output meet every deadline. So to make it cater to the streaming application, we make the input chunk pretty small. On the other hand, we also need to make the diffusion transformer really fast. So we also design our own KV cache strategy. And we also wanted to serve larger model. So we also design a pipeline parallelism. At the same time, in streaming application, it usually happens that we want to handle the high-speed motion videos. So we also design our own node scheduler to handle the high-speed motion videos. let me dive into several techniques into the StreamDiffusion V2. So we find that the given videos always have different motion speed. For example, we utilize very efficient motion estimators to estimate the input to estimate the motion speed of the input videos. And we could utilize some technique to translate this motion into some noise scheduler. For example, with the motion capturer, we can translate this motion into different noise level. The key idea is that the more motion changed in the video, the less noise we want to add into the original video. In that case, we could handle the high-speed motions. And we find this pretty useful for high-speed motion live stream. For example, this is the left video shows that our StreamDiffusion V2 without noise controller, and the right video shows that we utilize with noise controller. So you can see the left video is pretty blurry, but in the right video, we can handle the high-speed motions. And we also utilize for some video-based live streaming application. For example, we can do live streaming for our pets. So we can transform the bird into different kind of very cool styles. Yeah. And for human users, we can also translate the man into cute girl, and he's my intern actually. Yeah. And you can see that the users could send a prompt, and after we send a prompt, our model can quickly interact with the model and change the video output based on the prompt. Compared to previous StreamDiffusion V1, our model has better temporal consistency. Yeah. Yeah. Okay. Yeah, and after we release StreamDiffusion V2, we also go through some Twitter, and I noticed Eric said in Twitter, too long, don't read. V1 is more expressive, V2 is more consistent. Yeah, so it looks that compared to StreamDiffusion V1, our StreamDiffusion, even though it's more temporal consistent, it looks less expressive. So we want to consider this. So we want to improve the current model to make it more expressive as well. To enable it more expressive, this means we should enable high resolution. We should use larger model to enable more fancy and more great text prompts. And we also need more time steps to deal with the video. On the other hand, this means we also need some more flexible workload. There are already some techniques try to tackle it. For example, for some tensor parallelism technique like unices and real attention. So we try to utilize the unices and real attention to make it handle the larger resolution, the larger model, and more steps. But it does not that work because in unices and real attention, we require the activations in the model. The activation means the middle results in the model to translate to transit between the GPUs. So this additional overhead makes us hard to orchestrate current video diffusion models. So we design our own parallelism technique here. So we propose a parallelism technique plus our stream batch technique. So in our technique, given the first frame chunk comes in to the first GPU, and we will send it to the second GPU. At the same time, the second chunk comes in. So we could use the first GPU to deal with the second chunk. At the same time, the third chunk comes in. So we could put the first chunk and third chunk together and denote them together. And let's remember, stream batch could extremely improve the throughput. So leveraging this technique, we could leverage the stream batch technique and our parallelism technique, we can enable like users to utilize more GPUs and serve like larger mode and more higher resolutions. So we can make the 14. So utilize our work, we can make the 14 billion video models run up to 61 FPS. So this is a very fast speed. So you can see the demo that compared to the StreamDiffusion V1, we could enable more expressive videos. Yeah. Yeah, so, yeah, and so we combine all of this technique to design our StreamDiffusion V2, and all of our work was open sourced. And finally, I want to take some few minutes to express my acknowledgement to my advisors and our collaborators in both StreamDiffusion V1 and V2 and StreamV2V. And I also express my great appreciation to LivePeer to host these events and give us the opportunity to chat together. Yeah, thanks. That's all.